Hey everyone, and welcome. Today we're diving into one of the most elegant and honestly mind-bending ideas in all of physics. We're talking about the deep and often shocking connection between symmetry and the fundamental laws that run our entire universe.
All right, let's kick things off with something we all sort of remember from science class. This idea that certain rules in the universe just seem to be absolute, totally unbreakable. For example, we're all told that energy can't be created or destroyed. It just changes form. But have you ever really, truly stopped to ask, why? Why is it that the total amount of energy in a closed system is always, and I mean always, the same? It seems like such a simple question, but the answer? Well, the answer takes us right to the heart of how reality itself is put together. And look, it's not just energy. The total momentum of a system, its amount of motion, that's also perfectly conserved. These are not just helpful hints or suggestions. They are ironclad laws that work everywhere, from a tiny particle to a massive galaxy. But just saying, well, that's just how it is, that's not really a satisfying answer, is it? There has to be a deeper reason. And it turns out, there is. The secret, the beautiful and powerful answer to this whole puzzle comes down to a concept you might think you know, but in physics, it's so much deeper than just aesthetics. That concept is symmetry. So in physics, symmetry isn't just about, a butterfly's wings looking the same on both sides. A system has a symmetry if you can do something to it, if you can transform it in some way, and its core properties stay exactly the same. The key word here is invariance. It's about what doesn't change. Here's a really great way to picture this. Imagine the laws of physics are written down in some kind of cosmic rulebook. Now, if you can do something to your system, like, move it to the other side of the room, and the actual text in that rulebook doesn't change one bit, well, that invariance, that symmetry, it forces a specific quantity to be conserved. This connection is without a doubt one of the most powerful insights in all of science. Okay, so let's take this idea and apply it to the most fundamental things we know, the very fabric of space and time themselves. What happens when we use this rulebook idea on reality itself? First up, space. One of the wildest things about our universe is that one chunk of empty space is pretty much identical to any other chunk of empty space. The laws of physics work the same right here as they do billions of light years away. Physicists call this the homogeneity of space, or, a bit more simply, translational invariance. And here's the punchline. Because that cosmic rulebook is the same everywhere you go, the total linear momentum of any isolated system must be conserved. That's it. That's the reason for this fundamental law. It's a direct result of the symmetry of space.
Okay, so let's play the same game, but now with time. Just like space is uniform, time is too. The basic rules of the universe are the same today as they were a billion years ago, and they'll be the same a billion years from now. They are, as far as we can tell, eternal.
So what's the consequence of this symmetry? Well, it means that if you run an experiment today and then you repeat the exact same experiment tomorrow, you're going to get the same results. And because the rules don't change over time, the total energy of a closed system has to be conserved. That is the deep, fundamental origin of one of the most sacred laws in all of physics. This table just lays it all out so perfectly. The fact that the laws are the same everywhere in space, that gives us conservation of momentum. The fact that the laws are the same at all times, that gives us conservation of energy. It's just such a clean, direct, and absolutely beautiful connection.
So far, so good, right? The symmetries of space and time seem totally perfect. But let's try a different kind of symmetry, one that's a little more intuitive. What happens if we look at the universe in a mirror?
In physics, this idea of mirror image symmetry has a name. It's called parity, and it asks a really simple question. If you watch some physical event happen, and then you watch its perfect reflection in a mirror, is that reflected event also something that could possibly happen in the real world? Basically, does nature care about left versus right?
So you'd think, based on everything we've seen so far, that the answer would be a definite yes, right? If some process is possible, its mirror image should be too. That cosmic rulebook of ours shouldn't change just by looking at it in a mirror. Seems logical.
Wow. This is where our story takes a really dramatic turn, because that seemingly perfect, symmetrical picture of the universe, turns out it's got a crack in it. A crack in the mirror. Now, for almost everything we deal with, the answer is yes. The laws of gravity, of electricity and magnetism, and the strong nuclear force that glues atoms together, all of them are perfectly mirror-symmetric. They do not care about left versus right. But there are four fundamental forces, and one of them, the weak nuclear force, well, it turns out it plays by a completely different set of rules. It's a rule breaker.
Here's how this plays out, and it's pretty wild. In a certain kind of radioactive decay that's run by the weak force, an electron gets shot out. Now, electrons have this quantum property called spin. You can kind of picture it as a tiny little compass needle built into the particle. What scientists found is that in these decays, that compass needle always points in a specific direction relative to how the electron is moving. But the mirror image version of this, where the needle would point the other way, it is never, and I mean literally never, observed in nature. The universe on this deep level actually has a preference. It can tell left from right.
I mean, can you imagine discovering this? It was just absolutely mind-blowing. First theorized in 1956 and then proven with an experiment, it showed for the first time that the universe isn't perfectly ambidextrous. And here's the really important part. It proved that the absence of a symmetry is just as meaningful as its presence. It tells us something incredibly deep and, frankly, strange about the nature of reality.
So, let's wrap all this up and take a look at the grand design here, at the foundational role symmetry really plays in our universe.
This right here is the biggest takeaway of all. Symmetries aren't just some cute, aesthetic side effect of the laws of physics. It's the complete opposite. Symmetries are the deep, foundational principles themselves. The existence of a symmetry dictates what the laws have to be. The uniformity of space doesn't just happen to conserve momentum. It requires momentum to be conserved. This idea is so powerful, it's actually how physicists hunt for new laws of nature. They start by guessing what the underlying symmetries might be.
There's this wonderful line from the physicist R. Schenker that just captures this feeling perfectly. It's this idea that even when we feel like our knowledge is so tiny compared to the vastness of the universe, these symmetry principles are a kind of comfort, because they tell us that what little we do know is universal and will last forever.
And that leads me to one last thought to leave you with. The discovery that one simple symmetry, mirror symmetry, was broken opened up a whole new chapter in our understanding of the universe. So it just makes you wonder, right? If finding a single crack in the mirror showed us so much, what other incredible secrets about reality are still hiding out there, just waiting to be found in the symmetries we haven't even begun to fully understand?